Hello. 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 So just a couple of logistics before we get started. So assignment 3 submission was due yesterday. So how was the any issues with the assignment? So we'll actually cover quite a bit about the assignment 3 today. I mean, so you already tried implementing ROC curve and so on. But we will talk about the nitty-gritty nuances related to ROC curve today. Okay. So what I'll do today is also that assignment 4 is released. So I'm going to briefly discuss that, and then we'll get into model selection and assessment that we've been doing since last lecture. Okay. So we are here. Okay. So as you can see, the number of lecture slots is kind of reducing, which is, I guess, not good in terms of the at least in terms of the material that you want to cover. So but also, so let me pay attention to one more thing, which is a couple of slots reserved for project presentations. Okay, so this class is slightly different format than the online class. I guess we both have project components, but the online class is more about quizzing and so on. But here it's homework based. But at the same time, there's a big chunk of grades related to project, right? I hope I met most of you online yesterday. Somebody didn't show up, you know, you should have. But so focus on the fact that the project, you know, presentation for your team could be a week earlier than you would expect. Okay, so the slots are not given here yet, but we'll give them soon. But one of the teams is so one set of teams are gonna present 1 week before the second set of teams. Is this date? I think one of the dates is probably off, but yeah, so basically 2 weeks are reserved for project presentations. And so it's important that you have something tangible, interesting to present to your you know, peers, okay, in the class. And the report is due 1 day before, for every team is due before 1 day before 18th. Okay. And so let's talk about assignment 4 now. I'll go into the details, but in terms of scheduling, it's due about 20 days from now. But that's because one of the weeks is spring break week. Okay, so which means that you should try to finish the assignment, you know, ideally before you take a break. So try to pace yourself accordingly. And then there's a couple of weeks. Yeah, so 3 weeks to assignment 5. Okay, so there seems to be a question. Shifting the assignment submission deadlines to Monday. Yeah. Yes, so we can do that. Somebody was supposed to email me last time. So, okay, so why don't you, Shravya, just email me and I can set up the times. Okay, I'll change the times here. So, with that, let me comment. Okay. So let me go back to assignment 4. Okay. So any comments about current logistics? I just mentioned, hey, there's a project coming up and there's a spring break, so just pace your assignment work accordingly. Anything about that? We'll get into the details of assignment 4. So I think assignment 2 probably was really challenging compared to assignment 1, but assignment 3 was not as challenging, is what I would expect. I hope it is. So the challenging part of assignment 3 is probably that you're working with logistic regression, but you also have to kind of work with ROC curves and stuff, which you have not seen in the class. Today we'll cover that. But was there anything super difficult about assignment 3 compared to the first 2, for example? No, right? So I strongly encourage everybody to do it yourself. Okay, so even if you're in a team, try to work on each part. It's supposed to be like a solo journey, ideally. So try to work on each part yourself, and that's how you'll kind of become proficient in Python and working with these types of Python data structures, basically pandas and so on. Okay. So okay, let's talk about assignment 4. This is not. Okay, assignment 4 has a few parts which are basically related to linear models, and then SVMs. Okay, so let me briefly comment about SVMs. SVMs actually appear in lecture slide number 6 and number 7, which we will not cover. Okay, so I'm planning not to cover 6 and 7 because so how many of you have actually done 572 before? Okay, some of you. So, or all of you. Have you anybody not done 572? Are you doing simultaneously? Okay, so SVMs are covered in that course as well. But you don't need to know the all sorts of background details of SVM. So here the objective is in assignment 4 to use a library, in this case scikit-learn, and so read its documentation and use the SVM implementation there. To at least the objective of assignment 4 is to kind of get used to the scikit-learn pattern, and which you might have already seen. It's basically pre-process and then dot fit and dot predict, kind of a template that you'll see, and actually not just the scikit-learn score models, but many auxiliary packages that you might have seen. They try to fit into this format, okay, which is pre-process, fit, predict. Okay, so the objective of assignment 4 is to work with SVM models, and then SVMs happen to be binary classifiers, very similar to logistic regression classifier. But for them to go from 2-class to multi-class, there's a little bit of nuance involved. Okay, that's where you will kind of try to spend some time on building that multi-class classifier. Okay, so there's an appropriate data set. So let me go linearly. So first we'll talk about generalized linear model. So this is just a exercise in trying out a slightly different generalized linear model problem instance, which is Poisson regression. Okay, so here it's count data. So just like you were able to deal with binary case, binary logistic regression case, regression case, regular regression, which was a normal distribution assumption. And then we also looked at multi-class logistic regression, which is essentially categorical distribution assumption. So Bernoulli normal and categorical distribution assumptions led to certain link functions, and so we had a model and an appropriate training algorithm. So here the assumption about the target variable is that it's Poisson, so it's a count, it's a positive integer value data target value. So given that, you can try to you'll have to use this type of distribution, which is a Poisson distribution's probability density function. So you'll just kind of work through the how does it fit, how does it belong to an exponential family, and if so, then what would be its loss function, what would be its likelihood and things like that. Okay. So it's an exercise, since we have seen 3 examples in the lecture notes, so hopefully the 4th example, which is Poisson regression, should not be complicated. So this is not related to coding, so this is mostly verbal answers. Okay, just the second question is about is a toy example, very similar to, I think there was a toy example in the previous assignment as well. Here it's a very small data set, 7 data points, so no test train and all that stuff. It's just 7 data points, and we want to figure out we want to kind of understand how an SVM classifier can work on this type of data. So if you go to SVM documentation, of in scikit-learn. You'll see, for example, so the purpose of this assignment is actually go through documentation. It's a very important skill to develop. It's like a textbook or a chapter or a section, but it has a slightly different, way of narrating things. So, for example, the simplest example for a scikit-learn model is right here, right? So it's like import a model. Here's my data, XY, features, two-dimensional features, one-dimensional target, and then you're calling a model. And then, so building a particular object from the model class, and then calling a fit function. Okay, and that's it. So there are 4 lines to get SVM model, right? So it's very similar to that. So assignment 4 is just saying, hey, instead of that data, that x comma y in that example, x comma y happens to be a little bit bigger. It has 7 data points instead of 2 data points in the previous example. But asks you to understand, like what the built model looks like. Okay, so for that you should pretty much just rely on the notation, the data, sorry, the information that's provided in the documentation. Okay, so for those who have done 572, I guess it's a little bit of advantage, because you might have seen what are some discussion about what are support vectors, pretty much what are support vectors. But there's some they're basically just question about like what is the linear classifier here and what does its expression look like. So if you really think of it in terms of linear model, since it's a linear model, SVM is a linear model, it just gives you a linear decision boundary. Okay, so it's a 2-class classification problem here. The output variable is y or n, so it gives you a linear decision boundary. If it's a linear decision boundary, it has to be represented using what is called a hyperplane. Okay, or in 2 dimensions it's going to be a line. Okay, it's a hyperplane or a plane in 3 dimensions, and so it will have its own equation. Okay, some coefficient like theta naught, theta 1, theta 2, and theta naught. You just need to figure that out for this data. Okay, you can actually manually do it, but I would suggest use the scikit-learn documentation page to kind of guide you how to answer these questions. And the next question is really about, again, using this support vector classifier as a black box and work through a particular instance. It is basically a natural language processing task, where the task is to classify 4 classes. Okay, there are 4 classes in this data set. It's a supervised learning problem, multi-class classification problem, and the feature vector happens to be what is called a bag of words representation. And so that information is given here in this question. So what is bag of words and so on. You have to, the kind of exercise here is to kind of parse that CSV file. It's not exactly read_CSV of pandas. Okay, it's going to be slightly different. So for example, here's one line in that text document. Okay, it doesn't look like a comma separated value, but it's some compressed format. Okay, so we're parsing this and then building multiple binary classifiers. Okay, so we, support vector machine or support vector classifier, at least the core version or the default version or textbook version, is basically binary classifier. So we'll build a bunch of binary classifiers and then use that to do this 4-class classification problem. Okay, and all the information related to how to do that 4-class classification is given in the question. I mean, it's very natural, right? If you can only build binary classifiers and you have 4 classes, you can either do, you can do every pair of classes, one versus the other, and then you'll have like 4 choose 2 number of classifiers, and then you can take some sort of majority or something like that. Okay, so those types of intuitive heuristics is exactly how you do it, and so that's what's given in this question. Okay. And again, all this doesn't rely on knowing all the nuances of SVC. In fact, this question doesn't require much of the details of support vector classifier. You can actually swap it out and use logistic regression if you want, behind the scenes, right? Instead of the binary classifier being an SVC, you can change it to logistic regression if you want. But so that's what this question is asking, like work through building this multi-class classifier using this SVC base. Okay, and there's several parts to this question, but if you come to okay, I think I'm missing. Okay, I think indexing has kind of messed up, so I will fix it right after this. But basically, it turns out that in the scikit-learn page itself. So actually, you can do that multi-class classification here by using using an extra argument, okay, while defining the function. So this is something that you will test. So it's just like in the previous assignments, at the end of one of the questions could be, hey, test it against scikit-learn's implementation, right? So here you will test against scikit-learn's implementation, one versus all, one versus one type of a situation. Okay, so I mean, once you get to the questions, you will see the details. But any questions at the overall scope? So it's basically looking at generalized linear models, trying out Poisson regression, and then trying out support vector classifiers as the base for a multi-class classification problem, and then a toy problem. Yeah, and of course, as a part of the support multi-class classification, there's a notion of holdout validation, and that's something that we have seen last lecture. I'm going to talk about it today as well. Okay. Yeah, but in the lectures, I'm planning to not cover SVMs in detail. Although there's like lecture 6 and 7 slides, which are about a lot of details about SVMs. We'll directly go to generative models and unsupervised learning next lecture onwards. Okay. Any questions? I don't know if there's any questions. So question 2, do we also have to use a Scratch or just okay? So we have to use a scikit-learn model there because we haven't discussed how to so how to build a how to write it from scratch. Okay, we haven't seen the internal details of SVM, at least not today. Next lecture we'll briefly discuss it, but that may not be enough to write it from scratch. But if you are interested, you can write it from scratch as well. It's fine. Okay, so with that, let's actually that's all I had to say about the logistics. And so we'll come back to, if you look at the list of topics, actually, let me briefly mention this. We are here. Okay, so this collection of topics is just an exhaustive list. Doesn't have to, it's not. In fact, it was not my expectation to cover everything. My interest is in covering, some subset of them and in a lot of details. So the most important lecture is actually, today's lecture and last lecture, because really you can always call a package, fit a function, right? But really to understand whether that function is doing something that you desire, whether it's overfitting, for example, and is going to do terribly in production, for example, is kind of hard to discern. And in fact, it's still hard to discern today in 2022 when you communicate with business stakeholders and non-data science folks. But it's good to have a good training in the set of topics that we'll see today and what we saw last lecture. Okay, but if you look at the rest of the topics, we'll probably not spend time here, and we'll directly talk about some generative models and so on, and also talk about unsupervised learning, some of the initial topics there. Okay, so that's the plan for the second half of this, so this month and next month. So I'm starting with slide lecture 05. If you remember, if you watched the video or if you remember from last time, I was looking at lecture 04B. Okay, so I was talking about how to estimate, how to get a sense of how would a classifier do in production or in test, basically. Okay, so it turns out that 4B and lecture 5, they have kind of an overlapping set of slides for the first 30. In fact, it's exactly almost the same slide. So I'm just, instead of repeating 4B, I've picked up 5 directly. Okay, it's exactly the same set of slides. Okay, so just so that you're not confused of where we are, we're not abandoning where we left last time with 4B. In fact, we'll recap from earlier than where we left off today. Where is this? Yes, no. I don't think. Okay, so recall from last time as well as this time, the overall context is really we want to do selection and assessment. Okay, and so the difference between selection and assessment is selection is between model classes, like something like, hey, I want to choose between SVM / random forest / decision tree / KNN. So that's different model classes or different models. And assessment is at the level of a hypothesis. Hypothesis, just think of it as a function within a model class. Like for example, here the model class is linear models, and then this red line here is one hypothesis. Okay, it is backed by one particular parameter value, like a slope and an intercept, right? Similarly, a different model or different hypothesis is this other line, okay, which is backed by a different set of parameters, but it's the same model family or model class. Okay, just to distinguish between these two ideas. And yeah, so there are a lot of different hypotheses, and here's an example where there are different model classes or models themselves. Okay, so for example, mth order regression is just in one dimension. Let's say we are in one dimension, so there's only one feature, and you're trying to fit a curve. For example, this the ground truth is this green curve, and you have samples which are noisy versions of that curve, which are blue. And then you can fit a first order regression model, which is just which is basically a line in 2 dimensions, or you can fit a 9th degree polynomial, which would be like this red line here, red curve here. And so there are 2 different model classes. Okay, they belong to 2 different models. It turns out, the best. So even though there are multiple models, model classes, like first order, second order, 9th order, and so on, there's still a choice needs to be made, like which model class is appropriate, and within that model class, what are the right coefficients to have. Okay, so it's like a 2-level question here. Okay, so choosing between model classes, and then once you zoom in on the model class, then what is the right parameter. Okay, so it turns out this is the model class, and then you can pick thetas appropriately. So in model selection and assessment, we are really interested in like how do we ensure one hypothesis is better than the other, how do we ensure that one model class or model is better than the other, and what do you lose by just picking one of them, right? You lose because you may be the thing that you chose, the hypothesis, and the model class it belongs to, maybe overfitting your data or underfitting your data, which may have consequences once you use it in production or in test, basically. Okay, and to kind of do this, answer these questions, what we have at our disposal is just the training data. There's nothing else, right? I mean, there could also be domain knowledge, then you can use that as well. So for that, to answer these 2 questions of how do we pick the right hypothesis, how do we pick the right model class, we want to formalize with some notation. Again, this notation is just a shorthand. As I said, you can write the same thing in English. So example, so we're gonna make some assumptions actually implicitly here. So we have an example x, y, and there's a joint distribution between this the input and the output. Okay, so we probably just looked at conditional distributions. If you remember GLMs, we were only talking about the distribution of y. We didn't say anything about the distribution of x. Okay, so x can be whatever. But here we're going to talk about the joint distribution between x and y, okay, as the underlying assumption. But it's basically just to formalize how we think about performance in test or performance in production. Okay. So training data, which means our training data, both x and y, are identical and independently distributed. Sorry, independent and identically distributed from this underlying unknown joint distribution. Okay, and then you can have a loss function, which is actually a function between. So this loss function just measures the discrepancy between if you have a hypothesis. Okay, so ignore this delta here. So it's delta of h of x comma y. It's basically saying, hey, h of x is saying something, and what y is saying something. So how big is the difference between them? Okay, so if h of x is predicting the same as y, for example, then your loss should be low. For example, here 0, 1 loss is exactly saying that. If h of x, which is a, is equal to b, then the loss is 0. Otherwise, it's 1. Okay, so it's a 0, 1 misclassification loss. And so what we care about is actually this quantity shown in this slide, which is the error of a classifier with respect to this underlying joint distribution, which we don't have. Okay, so we don't have that object. Okay, generally we only are getting training data, so we don't have that object, but we care about how does it perform with respect to the joint distribution. Okay, so that's defined like this, and you can have expectation. Right here, there are some nuances, right? So why is this an expectation of loss? Okay, why can't it be some other function of the joint distribution. Okay, so I don't want to take a tangent there, but you can ask, like, why do I care about the expected performance of this, of this classifier? Why can't I worry about like tail risks or something? Okay? Something where you're doing catastrophically bad. That's what I want to minimize, for example. Anyway, so but for us, for now, it's expectation over the loss, and that's defined. If you have discrete random variables like x and y are just discrete, then it's just a summation, and this p is just the joint distribution is just a probability mass function, okay, of every pair of values that x and y take. Just sum it up. Use this weighted sum right here. Okay. And so this is called generalization error or test error, and generalization error or true error, or you can also call it test error. But basically, you don't have access to it. Okay. So of course, if you have a test data set, you can do something, but let's just call it generalization error / true error, and you don't have access to it. Why do we don't have access? Again, we don't know the joint distribution. But we have data. You may say we have data. So data is probably corresponding very similar to the underlying distribution. So why do we care about this difference? Okay. And that's exactly the problem. Okay. So the problem is exactly that we have data, which is a IID sample from this joint distribution, but the whatever we estimate, like models and whatever error scores and so on, it's all from this data. But the data may not be, like for example, if you draw samples from, let's say, a unbiased coin, okay, like it's 50% heads, 50% tails. Maybe it turns out in one realization that it all landed heads. Okay, so does it mean that like if it landed heads all the time, let's say 10 flips, do you know anything about the underlying distribution? No, right? So there could be some realizations for which the data doesn't say much about like what the underlying distribution is. So that's why there's this discrepancy between you have training data, which is sometimes inadequate for talking about the underlying distribution. So this gap is what is causing the concern here. So if you have for any data set D with m examples, you can talk about the error D, and here so error of any given hypothesis H as some normalized sum like this of the same loss function that we define over the data. Okay, so if this data is the training data, it's called the empirical loss or the or risk. Okay, empirical risk or empirical loss or sample error. Okay, just to contrast it with the generalization error or true error, okay? or the expected loss / risk. So expected loss, empirical loss, sample error versus order or generalization error. Okay. Okay, so as I said, there's some underlying process. So process just means process just means there's an underlying distribution here. Okay, so it's just some real world phenomena is going on, which can be summarized using this joint distribution, which itself is a big approximation. But let's say there's a joint distribution. What we observe is data, which is the train, from which we learn some model typically. Okay, and we'll talk, and you've seen several models so far. Typically, we learn a model H. Okay, and let's say we do have access to some additional data, okay, which we will not use in test, okay, which is good because then at least this, the H was derived from this data. So H is an estimator. It is a function of this data. Okay, but at least this H is not a function of this data. So from the perspective of this test samples, this H is, it doesn't matter whether H was based on some previous data or not. Okay, so this H is kind of independent of this data basically, because this H depends only on training data. Okay, and then you can use H and test samples to get an estimate. Okay, of how this H can do, how this hypothesis can do. Okay, so that's the idea behind what is called holdout cross validation, which is part of assignment 4. So what we do here is, given the full collection of data that we get, capital D, we're going to break it into a couple of parts. Okay, this is by the way, is an elementary step towards k-fold cross validation, which many of you already are familiar with. But let's really understand the nuances with this, okay? Because there's a lot more complicated nuances with k-fold cross validation, at least in terms of why is it the right thing to do. Of course, in terms of practice, you can always implement k-fold cross validation, get some model numbers, and just move on with your life. But there is some pitfalls with these procedures. So that's why we're delving deep into what is the nuance, like why are we doing this, right? So let's say holdout cross validation is just about holding out a part of the data which you don't want to use for training, but you want to use it for evaluation. Okay, so So let's say 30%, you call it D val, D subscript val for the validation data. And so what you do is basically, as we saw in the previous slide, we compute a H hat. We're putting hat because in statistics, generally estimators are estimated from data from a sample, and so the convention is to generally put a hat. Okay, it's a function of the data. So how do you get H hat? You kind of do some optimization, so minimize some, for example, training loss. Okay, the square loss that we saw in the first lecture and so on. And then once we have H hat, we have D val, and so we can use these two to get a sense of how does H hat perform on this validation data. Okay, and the hope is that this error D val on the H hat is basically a proxy, is an approximation for error over the true underlying distribution. Okay, so that's the hope. So use this as an approximation for the true underlying distribution. But so that's good. It's an estimation. But we want to kind of claim a couple of additional things, which you generally don't see in practice, but it's good to know, is that you don't want to just say that, hey, this performance is a good indicator of how it would perform in production, but I can also tell you what my confidence is with respect to my estimate. Okay, some confidence intervals, basically. So generally, when you report, for example, let's say you have a bunch of data points and you estimate the mean. Let's say you're estimating, let's say, the mean of a Gaussian, standard Gaussian, not standard Gaussian, sorry, mean of a Gaussian with variance 1, variance is fixed. You have a bunch of data points. You can estimate the mean, but you can also tell me, how much off you could be. Like you report confidence, right, of how good you are. So we want to compute confidence intervals about our approximation as well. Okay, so that will kind of really give you, hey, my estimate is this error D val of H hat, and I can based on that, I'm going to compute an interval, and then that interval will kind of tell me that whatever this H hat has performance with very high confidence between these two numbers. Okay, so that's the idea. We want to get a bracket within which the true performance of H hat lies in. Okay, so let's actually talk about that. So let's say we are learning a classifier H hat. Let's say spam classifier, doesn't matter. So some H hat, and ideally what we want is we want to build a model which has hopefully less than 10% error. Okay? So we want 10% error in the population. So we want to claim that, hey, I have built this H hat using training data, and it's gonna not make error greater than 10%. Okay, we're gonna make a claim using a confidence interval. Okay, so we'll say we'll use confidence interval in a second. But so let's say in observation, which is this D val that is used for the holdout data set, the error in D val happens to be 10 by 500. So happens to have 500 data points in this D val set, and there were 10 errors that this function made. Okay, so I'm looking at just these numbers. You can say, hey, the performance on D val is 0.02, and I was aiming for 10%. It's actually 2%, so it's good. Okay, I can stop my process right here and say, hey, this 0.2% is probably the performance of this model, so let's stop. Right? No, but the idea is to go beyond this means. So you want to build a confidence interval within which, for example, if this true performance lies, then you can kind of go ahead. Okay, so let's think about that for a second. So what we want to say is this key question. Okay, for the next few slides, you'll see a lot of manipulations, but ultimately what we want to say is the following. We got some error D val 0.02. Is this significant evidence for claiming that the population performance of my model is less than 10%? So we got some evidence. So we have some hypothesis. We got some evidence 0.02, some hypothesis. The question is, what is this number significant evidence for saying that this error is smaller than 0.1? Okay. If so, for example, so think in terms of hypothesis testing idea, right? So we have some reference. Okay, we think that it should be 10%, but we saw something really good. So we'll say that the probability of this really good number happening under this baseline assumption of 10% is very rare, and so which means that there is a good evidence that my true performance is less than 10%. Okay? That's the idea. So this is really the key point we want to drive. Okay. So and it's not a so what we're doing for the next few slides is not really a academic exercise. It's really the question is, where do you stop, right? So you can always stop at these two lines, as I said. You don't even care about the first line. You just say, hey, validation error is 2%, and done. Your workflow can end right there in practice. But given that your validation error is 2%, what is the interval that you can tell me where the true error lies? That's the extra effort that you can put in, which can kind of really build more confidence in your model, right? So that's what we're doing here. So how do we do that? We actually map this performance numbers to a binomial setting. Okay, so binomial setting. So typically, all these hypothesis tests, they have an underlying, not all, but like a good chunk of them have some underlying assumption. So the assumption here is we're going to map what we saw in the previous slide for how we performed on dval to this binomial distribution, to a binomial distribution. So what is the binomial distribution? We know it's like basically number of trials and the probability of heads in each trial. Okay, and that's what kind of parameterizes binomial. So and here is a quick description of its probability mass function. So m is the number of trials and phi is the bias in each trial. Okay, and binomial distribution is the distribution of the count of number of heads, for example. Okay, so it has some expression that's not super important. What's important is we're going to map it to what we saw in the previous slide. Okay, so what we're going to say is that phi, which is the unknown, which is the bias of the trial, each trial is going to be this underlying unknown error rate, error value. Okay, error over the true distribution. And then m and y are just going to be the number of examples in my validation, and y is going to be the number of errors in the validation, number of errors that we observe. Okay, so you can think of it this way: if the true error value was something, okay, let's say 10%, then I should be seeing 10% errors. Like, so each observation, remember, is the IID. So it's like flipping a coin. So this classifier has 10% error possibility. Then each observation should be making an error with 10% probability, right? So that means you should see roughly like 10% of them should be erroneous, okay, erroneous predictions. But the number of error observations we actually see is probably 2, okay, or whatever is that 2%. Okay, so now the question is, under the error probability that we care about, which is like 10%, what's the likelihood that we saw like this much lesser number of errors? Okay. So null hypothesis is that phi is, let's say, 0.1, and we have seen 10 errors out of 500 validation examples. Okay, so we were asking what is the probability that y is less than or equal to 10. Okay, this is exactly the hypothesis test situation. So what's the likelihood of seeing this observation and things rarer than it, given that number of trials is 500 and the underlying base rate or the bias of the Bernoulli is 0.1. Okay, so that happens to be some really small number. So it's rare to observe such small errors, which is less than some threshold. Okay, the alpha threshold, which is like 0.05. And so based on that, you can reject the null that your underlying error rate is like 10%. So okay, so that's how you can say that it's not going to make, and not just 10%. If you make it higher, like 20%, 30%, definitely you continue to reject. Okay, so that's how you say that in reality you will not make higher error. Okay. Any questions about this part? Okay. Again, as I said, I will keep repeating the sentence. The objective here is not just report a validation number, even if it's k-fold cross validation or this folder validation. It's not just to report the validation number, but to give the confidence bound. So you're producing a validation number, but in addition to that, from there you're doing extra processing, which is producing two numbers, and then you're saying, hey, whatever is the true performance in with the underlying distribution, that's going to be between these two numbers in the interval. Okay, that's what we're trying to get to. So here there's no interval yet, but we'll show an interval in a second. In fact, right now. So what we're going to construct is basically a binomial confidence interval. So which is an interval around. So it's an interval which is derived from data. Okay, from the training data. From the validation data, such that the interval is basically can change if the validation data changes. But hopefully that interval overlaps with the true error performance of this classifier 95% of the time. Okay, so that's the kind of that's what we want to get to. Okay. So how do we do that? So we have, let's say we slightly change the example here. So instead of I think 10 errors out of 500 examples. Let's say there are 9 errors out of 40 examples. Then the question is like, what is the interval within which true error lies with 95% confidence? Okay, that's the interval question. So what we can do is, what we observed is 9 out of 40 examples. So what is the binomial? So what is my estimate of the binomial mean and the binomial variance? Okay, so we're going to use, so we'll first estimate the binomial mean and variance. So binomial mean is going to be 9 by 40, right? The binomial mean is going to be 9 by, the parameter is going to be 9 by 40, and then the mean itself is the number of trials times the parameter, so m times p, so which is equal to 9 itself, and the variance of the random variable, your estimate of the binomial variance is going to be m times phi times 1 minus p. Remember from, you can just look up binomial distributions Wikipedia page if you want. So m times phi times 1 minus p, that's going to be a number like this, which is 6.9, some number. So you got some estimated mean and estimated variance of this binomial, assuming binomial distribution. And then you're saying we can make a normal approximation to this binomial distribution if the variance is greater than 5. Okay, so just try to make it simple. We're just going to make a normal assumption, which leads us to a statement like this. Okay, which is so the expected error is 9. Okay, that 9 because we made 9 errors in the validation. Okay, and I'm going to say, hey, I made 9 errors. So in reality, the number of errors will be 9 minus something and 9 plus something with high probability. I want to figure out what is that minus something and plus something, and that's given by the normal approximation. Okay, so if you have 95% confidence that you want, then there is a, if you remember from doing a z-test, there's a 1.96 number that comes in here. And then you have the square root of the variance, or basically the standard deviation of your standard deviation estimate. Okay, so which is just this estimate here. Okay. So that's how you get an interval. So what we did is we have the original h hat from which we got a validation performance, which is the mean here. Okay, e of y, but we also got the variance of the assuming the Bernoulli distribution. Assuming a binomial distribution. And then we made a normal approximation to say, hey, given that validation data, we can say that the true errors will be between some number on the left and some number on the right. Okay, which is it's the number of errors. So if you normalize it, which is divided by 40 here, then the true error is between 10% and 38%. So that's a claim you can make for this data. If you observe 9 out of 40 performance, which is basically something like 20% error, 25% error, then in reality your true error may be between 10% and 40%. Okay, that's the idea. Any questions here? Is everything complicated or easy? Let's see if there are any questions here. No. No questions? Okay, so I'll not spend too much time on the confidence interval because there was one approximation that happened, the normal approximation. But basically, what we want is two numbers, okay, PL and PU, which we get from the validation data. So H hat was obtained from training data. Using validation data and H hat, we get two numbers, P low and P high. Those are the two bands, two upper and lower values of the confidence interval. Okay, and so you want to say that the true error belongs to this interval with high probability, with 95% probability. And the two exceptions out of this interval is when, for example, the error can be lower than PL and the error can be higher than PU. So let's talk about I'll probably not spend too much time on this, but basically the point is, what is the probability of observing more than 9 out of 40 errors? That left-hand side tail is, if you remember, we use 1.96. That means that we are leaving a tail on each side, which is 2.5%, and that's why 2.5 and 2.5, and so remaining 95% is where we're getting the two confidence intervals, lower and upper values. So here we're just talking about what happens, like if you observe more errors, more than 9 errors out of 40 examples, then this if error p, so if the true number is smaller, okay, is smaller than 9:40, then then you being on the right tail is smaller. Okay? This number decreases. Okay, so PL is the lowest. Sorry, what's the right way to say this? So PL is the lower probability error rate, which is a number that you plug in here and say what's the probability of observing 9 errors out of 40 observations at PL if it is greater than 0.025, which is 2.5%. So the smallest value that you can plug in there, and that's the lower bound. And similarly, on the upper side, you're asking what is the probability of observing y smaller than y smaller than 9. What is the largest value that you can pick for the bias, and that's greater than which can lead to greater than 2.25%, and those two numbers are exactly what we computed in the previous slide. Okay? And here we're just interpreting them of what they mean. Okay, so these two numbers that you saw here, so 0.09 and 0.3844. So those are just the extreme values. Okay, so they're just trying to ensure that beyond that and below that, you will have a different confidence value. Okay, so that if you pick 95% confidence, then you have to dedicate 2.5% to the right hand side and 2.5% to the left hand side of the tails. Okay, I think this, yeah. So, but all these numbers you can compute using packages in Python or on computer. But here we just want to understand how do you get a confidence interval for the true performance of the model, okay? True performance of your hypothesis. Sorry. Okay, so let me just do another 2-minute discussion about a slightly different test, only because what we did is holdout validation. We had a holdout data and we said, hey, here's a confidence interval for a model. But what if you want to do a little bit more work, which is you constructed one model, one hypothesis, and then what if you come up with another hypothesis? Okay, so you use the same training data, but you got a different hypothesis. Okay, different linear model, for example. The question is now you ask like which, different logical regression model, let's say, and the question is now which one is better. Okay, so we're going to answer this question, slightly different question, again using the same data. So we have the training data and validation data, and you have two, let's say, learning algorithms or whatever. So at the end of the day, we got two hypotheses, H1 hat and H2 hat, and so we have two models or two hypotheses, and then we can use the validation data to come up with two numbers, right? So how would they do in validation, right? So error validation for H1 hat and error validation for H2 hat. Then what we can do is a slightly different test now, which is we can certainly stop here and just report these numbers and say, hey, one is better than the other. In fact, in k-fold cross validation, for example, you just report which validation error happens to be the lower. You maybe make that choice, right? Model choice. Here, what we want to do is a little bit more, which is a hypothesis test. Okay, is the two numbers, let's say validation numbers are 10% error for model 1 and 9% error for model 2. Given those two, is it statistically significant in terms of the difference, in the sense that are they really different? Okay, so one has 0.9% error, 0.9 error, the other one has 10% error. Are they actually different? That's what we want to answer. And the way we answer is we have a null hypothesis that both of them have the same error value. Okay? Both of them have the same performance in production. Okay, so with respect to the underlying distribution, both have the same bias. If you think of a Bernoulli distribution, okay, and then what we do is it's a particular test called the binomial sign test or McNemar's test, where what we're trying to do is look at validation data and see at which locations did the first hypothesis make errors, but the second one did not, and look at the examples where the second hypothesis made errors, but the first one did not. Okay, so maybe there are some bunch of examples where one did the error, but the other one did not. Okay, so let's say they are called y1 and y2. These are the example number of examples. Let's say. Then what we want is so the way we set up this test is say that if the null is that the true performance of both models is the same, then y1 and y2 are just like coin toss realizations. Like one of them should be heads, one of them should be tails, and the coin toss probability should be 0.5. So if you think of a Bernoulli model, if both are supposed to be the same, then half the time one of them should be better and half the time the other one should be better. Okay, so that's what's happening here. So we'll say the null hypothesis is driven by this binomial with 0.5, and the number of trials here is y1 plus y2. Okay, so because y1 was one where one did better than the other, and y2 is where the second one did better than the first one. Okay, so under this null, now what did you observe? You actually observed a particular value of y1 and particular value of y2. Right? So I mean, y1 plus y2 is sum up to the number of trials. So you can just focus on one of them. You can just ask, hey, given this binomial distribution, what is the probability of me observing like only 3 heads or only 1 head, whatever you actually observed, which is the number of places where one of the model did better than the other. Okay. So if that number is, you can compute the probability. If that probability is really small, then that means, it's a rare situation that what we observe, and therefore we can reject the null, saying that both the model's performance is the same. Okay, it's a very same idea as any hypothesis testing. Under the null, you observe a rare event, and because of the rare event, you kind of say, hey, I can reject the null. Okay. So you can do one-sided test, which is you just focus on y1 is less than little y1 given the underlying null hypothesis model, or you can test for just the or just on the second side, or you can do a sum like this. So that's called binomial sign test. Again, to just say that if you produce 2 models with 2 numbers, it just may happen that the 2 numbers are anyway approximations. It may just happen that both models have the same performance. Okay, so you want to kind of reject that, and that's why you're doing this extra test. Okay? It's very common in typical ML workflows to kind of stop at slight differences between models and say, hey, one model is better than the other. But you want to kind of do a test to say that, hey, the one model is actually significantly different than the other. Okay. Yeah, so let me skip numbers here because it's so this slide is just showing that for 2 performance numbers, sometimes you may not be able to reject the null, that hey, one has 1.15% error and the other one is 1.25% error, but we cannot reject the null that they both have the same performance in reality. Or sometimes you can actually reject it. So which is the second example here. So let me wrap up this part of testing. What we wanted to do is not just report validation numbers, but go beyond that. And so that's hypothesis testing. Hopefully, some of you have seen it in 570 or maybe even 572. I don't know. But what was the overall goal, right? So, goal was really to capture this. First of all, we made the assumption that it's joint distribution, and then we wanted to capture this performance of anything that we construct h hat, which is generally derived from data. With that we have access to h hat we constructed, but then what is its performance with respect to the underlying distribution? We don't have the underlying distribution. We only have the training data from which we constructed h hat. So that was intractable to directly measure unless you have lots and lots of IID examples from the P, which is what dval was trying to do. Dval, the validation data, the holdout data was trying to proxy the true underlying distribution. Okay, and so I guess this is what it's saying here. So dval, and we utilize dval as if d-test is kind of approximated by the performance on dval. Okay? So it's an estimator of on how it would perform in reality. Okay, so there are a lot of similar issues. Okay, so we may not have enough data to make big enough d-train and d-test or whatever dval. Okay, but we do want large d-test because that gives you a very good handle on how it will perform in the future. But we do want large d-train because large d-train means we have covered all sorts of potential features that can happen, and based on that we have potential supervisory signal, which is the labels also. Okay, so if you're in a large high-dimensional space and if you only have few examples, you understand that you cannot generalize well to regions where you don't have those feature vectors, right? So but that's the issue. We cannot have these too big, and single retrain cannot tell a sensitivity of accuracy to the training data. Okay, in the sense that one D-train produces one hypothesis, but we don't know like how it would perform if a slightly different D-train was presented. Okay. So these are the limitations of trying to get to this performance measure of any hypothesis. Okay. And this is just for the approach where we said we'll have one held out data set. Now you can imagine for k-fold cross-validation, a lot of things become much more messier. So it's not even easy to intuit and add this confidence bounds. Okay. But let's at least procedurally, the split between D-train versus D-test, as you saw, has limitations. You cannot have large D-train and large D-test if the original data set is fixed. So we're gonna fix that at least in practice by just doing exactly what you know, right? So we're gonna estimate this error performance in a little bit more robust way by kind of reusing our samples in a little bit clever way, which is exactly k-fold cross-validation. Okay? So let's briefly discuss this procedure. You have seen this potentially before. It's also part of assignment 4. So what we do here is, as the name suggests, we do compute a proxy for this error p, okay, error p of my hypothesis. So how do we do that? We randomly split our data set into k disjoint and equally sized subsets. So this is not super important that it has to be equal size, but roughly approximately same is fine. But basically k disjoint subsets, okay, d1 to dk. You can also stratify. Stratify just means like you're trying to control for some characteristics on each data set. So for example, you can stratify such that the number of positive examples and negative examples in each set, in each of the k folds is kind of balanced. Okay, you can do that as well, but you can also randomly just split it into 4 k folds. And then for each model, okay, so each model mi, so m subscript I just corresponds to each model. So just think of it as, let's say I have model 1, which is logistic regression, model 2 is SVM. So each model would be logistic regression model versus SVM model. Or it could be, think of those coefficients you are optimizing for in assignment 3, the regularization coefficient. So different coefficients means different models actually, okay, because so okay, let me not go into the reasoning, but different coefficients kind of define different models. Okay. So for each model, what you do is do a for loop over each fold. Okay, so j is from 1 to k. So if there are k folds, let's say 3 folds, then you'll have a 3-step loop here. And then what you do is you train your model, logistic regression / SVM or whatever the model is, on a data set which is all the data except for the jth fold. Okay, so you train your model on all data except the jth fold, and then you get some hypothesis. Okay, let's call that hypothesis h hat ij. Okay, I corresponding to the model, the model that we are choosing, the model class that we're choosing, and j corresponding to, hey, we skipped the j thing. Okay, so it's an easy notation here. It's just ith model and skip the jth data. We got some h hat, and then use that to estimate my error performance. Let's say the 0-1 misclassification or whatever the error is, on using only the jth fold. Okay, so it's like a Lee-1, not Lee-1, but k-fold cross-validation, where you use all the k-1 folds to train, and then use the train model, evaluate it only on the skipped fold that you have left out. Okay, that's the number, and then you do that for all the models, and then for, of course, the model for error, the estimate for test error. Okay, so this is an estimate very similar to how dval estimate for holdout validation was an proxy for the generalization error. The estimate for test error or generalization error is going to be 1 by k sum over k of each of these error values. Okay, so each of this held out performance, you're just going to sum them over. Okay, so there will be 3 numbers if you do 3 k. Sorry, there will be 3 numbers if you do 3-fold cross validation. Okay, so this is kind of clear. Has anybody any question about this computation procedure? Okay, so if you have such a choice, like if you have, so thing is, if you have an estimate for each model what could be a performance in reality, or generalization error, a proxy for generalization error, then you can say, hey, this model performs, like this in reality, this other model performs this in reality. So given such numbers, you can pick the one with the lowest estimated test error. Okay. So lowest estimated error. Once you get the model choice, then remember, in each model spec, you also have to pick the right hypothesis. And so you kind of retrain the model. Like, for example, let's say linear models are the best. Then under the linear model, you want to get explicitly the coefficients. And to get that, you use the full data set, because at this point, you've already chosen one of the model classes which you think is going to perform well. Okay. But okay, so here's an example for KNN. I'm not going to go into all the steps here, but you can see what changed is the second bullet point. Instead of model I, from KNN, the choice is K. Okay, so so think of K is equal to 1, 3, 5, 7, 9, whatever. So these are the choices. So you're trying to figure out for each choice how would it perform on the held out fold, and then you take an average. That's a proxy for how that KNN with that choice of K would have performed in reality or in production, right? And so you pick the K with the lowest estimated test error, and then that's the K you stick with when you do your KNN based predictions. Okay. So is that clear of how this works? Yeah, I mean, KNN doesn't have any further optimization, because once you choose K, I mean, there is no further hypothesis to be chosen, theta to be chosen. But if you're choosing between first order polynomial versus second order polynomial versus third order polynomial, the order is going to be your choice here for the for this for loop. Okay, so maybe the third order is the best one of the regression problem. And then once you pick the third order polynomial, then you have to pick theta naught, theta 1, theta 2 to figure out what is the exact third order polynomial they're going to use. Okay, so this is with respect to the regression problem that we saw at the beginning of this lecture. Okay, but so that's the computation procedure, and that's fine. You can stop right there. But the problem is that what we did for the holdout validation, the holdout validation procedure, which is really to understand, I have held out numbers, but can I produce confidence intervals and things like that? That's kind of super hard on for k-fold cross validation. So k-fold cross validation may say model 1 is better than model 2. Okay, you have two numbers. Okay, one is maybe slightly bigger than the other. Okay, that doesn't mean that the model choice with the lower number is automatically always going to be the best in reality. Maybe that it's just because of your data set that you are not able to distinguish between those two models. There is no way to have like a confidence interval here. It's not that there's no way, it's more complicated. Okay, because it's very difficult to compare. We saw how to compare hypothesis 1 versus hypothesis 2, like with the binary sign test, right? Instead of that, here it's going to be more complicated. Okay, so because especially the data sets are not, the models are not independent. Okay, so in the sense that the training sets for the models are not independent. So if you think of two steps of the for loop, this for loop, so let's say the jth model and the first model and the second model both have almost a good chunk of overlap in terms of their training data, so they're not themselves independent, and then they're being evaluated on data which is used in the other models development. So there's a lot of data being reused here, and that's what makes getting confidence intervals or this significance test harder. Okay. Okay, so that's on k-fold cross validation is exactly is a popular tool to do model selection, which is exactly this choice of a C, for example, in your if you're doing ridge regression or the logistic regression with penalty, the penalty coefficient. So those choices, you will make a discrete set of numbers typically, and then you try to pick one of these numbers based on k-fold cross validation or holdout validation, whichever works. Okay, but let's focus at the level of the hypothesis. You're not worried about the model, but you're worried about hypothesis 1 versus hypothesis 2. And the question is like, what are some metrics beyond accuracy? Okay, so accuracy may not be the only metric. So we will evaluate, we'll kind of focus on metrics now. And some of the metrics that you saw in assignment 3, and in fact, we worked on already, so that should make it a little bit easier here, is typically ROC, impression, and recall, and F measure, and so on. We're gonna not worry about this statistical significance aspect, which we saw while talking about generalization error. Okay. So let's start with before ROC curves and so on. Let's start with confusion matrix. Okay, you've already implemented confusion matrix, so I'm just gonna very quickly define, and especially since you've implemented it, if you have specific comments or questions, you should add it to the discussion. So confusion matrix is just nothing but an accounting and focused on binary classification, nothing but an accounting of how did your classifier do, right? So let's say, as you know, on the rows is the prediction, and on the columns is the ground truth. Okay, and it can be sometimes transposed, somebody pointed out, but let's focus on rows being predictions and columns being truth, which just means that the entry in the first cell is first cell just corresponds to, okay, there were some number of observations in my data which were actually positive, which were, let's say, positive class, and they happen to also be labeled as positive by my model. Okay, so my prediction is positive, prediction is true, and the ground truth is also positive. Okay? So in fact, if you look at the second word here, it's positive. Okay, so if you look at the row, the second word is positive, which means that the model's prediction is positive, and true positive just means that the ground truth is actually also positive, and that's why it's a true positive. Okay, the ground truth is not positive, whereas you are predicting positive, then it's called a false positive. Okay, so really the reference should be these positives and negatives. They're just corresponding to the prediction model. Okay, so true positive just means the model predicted positive, but happens to be also true, which is like you know. And so there are 4 numbers that you compute here. So these are the only things that can happen, right? Because the model is going to predict only 2 things, and there's only 2 things that can happen with the ground truth of each observation. And so there are 4 potential possibilities that whatever I predicted is the same as what the ground truth is, which is the diagonal things. So I predict true, and it's a positive number. I predict false, and it's actually a negative observation. Okay, so these are the good situations. And then the off diagonal ones are where I'm making a mistake. So for example, the ground truth is positive, but I'm saying it's a negative. Okay, or for example, here the ground truth is negative, but I'm saying it's a positive. Okay, so kind of having less off diagonal terms and having more bigger numbers on the diagonals is actually better. Okay, intuitively speaking. So let's take very simple example, classification of spam classification. So positive class is you kind of, let's say you are saying something is spam. Okay, is a positive class, and regular email is is everything else. Okay, then the true positive is exactly the number of spam emails that you actually truly classified as spam. Okay, spam emails that are actually classified as spam is true positive, and true negative is the number of regular emails okay, which were classified as regular, the diagonal guys, and which you want to be high. Okay. The off diagonal ones, false positive is you predicted it's a spam, but it's actually not spam. Okay. And that could be kind of risky. Maybe that email was let's say an employment offer, and it went into spam because the classifier said it's spam. So false positive is also called a type 1 error. And then false negative, which is you are predicting that it's not a spam, but it's a spam. Okay. Seeing an occasional spam in inbox maybe is not that risky, so I guess, but then it's called type 2 error. Okay. Yeah, and so just related back to that metric that we've been tracking quite a bit, the 0-1 classification error, or the opposite of that, which is accuracy. Okay, for binary classification, is nothing but a function of these 4 numbers, because these 4 numbers are just a summary of how did my predicted values line up with the true values. Accuracy is also the same, right? Accuracy is also how did my predictions line up with the true values. Every time it matches, it's good. Every time it doesn't match, the prediction doesn't match the ground truth, it's not good, right? So that's what's happening here. It's basically the diagonal numbers, true positives and true negatives, divided by however number of total number of observations we have. Okay, so if we have 50, 50, 50, 50, 200 observations, then maybe what is the number of times I've gotten it correct for each class, divided by 200, for example. That's accuracy. So any questions here? Okay, so I mean, the reason why we're going to look at several metrics now, and some of them, in fact, we kind of jumped, we kind of already dealt with them in the assignment number 3, is because there's some inadequacies of all these metrics. All these metrics are like summarizing, right? Summarizing the actual performance of the model. And so they may miss out some aspects that we would like to have. So let's look at this, which is accuracy adequate, right? So let's say, and this is actually exactly the issue that people bring up, especially people sometimes ask, hey, my data set is unbalanced. Okay, but imbalanced data set or unbalanced data sets, reporting accuracy may sometimes be misleading, which is kind of illustrated in the first point here. Let's say if our class labels are largely skewed, it just means that, hey, there are like 10 positive examples and 10,000 negative examples. Okay, let's say, or let's say here 97% are negative labels. Okay, then classifying negative samples, okay, falsely as positives is very bad, right? Because most of the data is negative, and so if you classify a negative sample, sorry, if you classify negative samples falsely as positives, it's very bad. Whereas classifying positive samples falsely as negatives may be okay. Which by which I just mean that if you have a if you're saying something is positive, but it is actually negative, okay. Am I correctly saying this? Okay, let me come back to this first example in a so actually what the first example is trying to say is that if you have 97% negative labels, then think of a dumb classifier, right? It will just say, hey, every example I'm just going to say negative. Okay, the class is negative. Okay, which means that I may be missing out on it's hard to kind of tag something as positive when most of my data is negative, basically. Okay, actually we'll spend some time on this, so let me interpret these sentences in the next slide. Let me talk about a slightly different issue. Okay, so why accuracy is not important, sorry, not why accuracy is not adequate. Okay, there were two aspects. One is kind of imbalanced data, which we'll discuss in the next couple of slides. And the second one is when there's a cost difference. Okay, there's a cost of doing a misclassification. Okay? So far our cost for misclassification is symmetric. If I misclassify positive as negative, that's still 1 point detected. If I misclassify negative as positive, so the underlying thing is positive, but I say negative, there's some cost, but so far it has been the same cost as if the underlying truth was positive and I said negative. Okay, whereas in some domains that's not the case. For example, in the medical domain, a false positive. Okay, so you predict something is there. Okay, let's say, for example, cancer is present. When it is not present, okay, will result in some cost for various tests. Okay, so that's okay. So false positive is at least okay. One side, one cost, this cost is fine. The second one, when it's false negative, okay, which means that you're predicting negative, whereas it's not negative, it's actually positive. Okay, so in the sense that somebody has cancer and you're saying it doesn't have cancer, may result in failure to treating the disease, right? So there's a asymmetric cost involved between for the off diagonal settings, okay, in the confusion matrix. So and so these 2 points are basically trying to illustrate that maybe accuracy is not, this one summarizing number is not enough. So we have 4 numbers, okay, and so not just those 4 numbers, we can create some additional functions of these numbers. Okay? So for example, true positive rate is just the number of true positives divided by the number of positive examples in reality. Okay? So let's say in the ground truth you have 30 positive examples. Okay, so that means the denominator is 30, and then you just look at how many of them did I get correctly. Did I correctly predict as positive. Okay, so that's the numerator, and that's called the recall, and it has it's pretty much related to information retrieval measure as well, which is also recall. So basically, it's basically the number of positive class sick people or spam who are correctly identified with that condition. So it's just this focus on the left column. Okay. And false positive rate is exactly the opposite. So basically, the number of false alarms that you've triggered, which is you predicted positive, but sorry, you predicted positive, but it was not there. So it was false alarm. And so how many number of false alarms did you trigger out of all the negative examples that you have? Ideally, for all these negative examples, you should always say negative, but for some you said positive. How many did you say positive? Ideally, the second number you want to keep as close to 0 as possible. The first number you want to keep as high to 1 as possible. Okay, that's the maximum number for recall. And so we will just play with these two and create a ROC curve, which you have already seen. But so let's in fact draw this figure where the x-axis is this false positive rate, okay, and the y-axis is true positive rate. Right? So these are the numbers. So we said, okay, we want to represent x-axis by FPR and y-axis by true positive rate or sensitivity, also called sensitivity, and false positive rate is 1 minus specificity. Okay, these are words kind of used to specify the performance of models, just like accuracy is used to specify the model performance of a model. Okay, these are just functions of that 4 numbers that we created. Right now, why we're drawing this box is it will become apparent in the next slide. So let's understand what's happening in this region. Okay, the square region. The x-axis is varying from 0 to 1, and y-axis is varying from 0 to 1, and that's because we saw in the previous slide the numerator is always like cannot be greater than the denominator. So the highest value these two numbers can take is at most 1, and the lowest value these two numbers can take is 0 when the numerator is 0. Okay, so what is this point 0, 1? So if you look at 0, 1, which is at the top left here, it's a point where the false positive rate is 0, okay, and true positive rate is 1. So whatever were positives, I got them. Sorry, whatever were the ground truth positives, I always said it was positive. That's great. That's the second bullet point. And false positive rate is 0, which means that whatever were negatives, I never raised the false alarm for them, which means that I always said whatever was negative was actually negative. Okay, which means that the off-diagonal numbers are actually 0. So if you think of the confusion matrix, off-diagonal numbers are 0, and that's this 1 here. Okay, okay. So that is actually a really good classifier, binary classifier. What about 0, 0? So 0, 0 is a model which is doing quite badly. Okay, it basically 0, 0 kind of corresponds to the situation where there is no true positive. Okay, the numerator for the true positive rate, right? The true positives, it's 0, which means that if there are 30 positives examples in my data, I'm never predicting anything to be positive. Okay, so that's a terrible classifier. And we're not talking much about the false positive rate in this example. Let's look at the next point, which is 1, 1. We are just trying to explore this region. So we looked at the top left, looked at the bottom left, now look at the top right. So 1, 1. So here we are always predicting everything to be positive. Basically, for 1, 1, the true positive rate is 1. So which means that if there are 30 examples which are positive, we are always predicting everything positive. But also my false positive rate is 1. Okay? Which means that of all the false positive rate is 1, which means that I am actually just I'm never predicting. So there's nothing on the bottom right cell of my confusion matrix. Okay, so I'm just there's no negative predictions, okay, basically. So there's no negative predictions for 1, 1, and there's no positive predictions for 0, 0. So just imagine that if I'm not predicting one of the classes, that means I'm basically predicting everything to be the same class. That's like a really dumb classifier, right? It's like doesn't matter what the input is, just return a constant value, right? So Okay, so then we want to kind of understand further, like, okay, we understood the corner points. What can we say about points, for example, which are, let's say, over here, and what are points about at the upper right, for example? Okay, so the points on the lower left have a low true positive rate, okay, which means that they're conservative. They're not willing to say more numbers, more of these examples are positive. Okay? They're only able to say some of them are positive. Okay, and points which are like on the upper half or basically upper right, they are kind of making a lot of positive guesses. Okay, so ideally, if you are right here, then you're saying everything that was positive, you're actually saying it's positive. Okay. So briefly, I want to mention this diagonal line, which is y is equal to x is actually a random guessing classifier. So let's say you guess 100 times a percentage of your examples as positive, okay, and yeah, of course the others as negative. Okay, so which means that let's say if you're guessing, let's say a, this number, this a is 1/2 or 0.5, which means that 50% of the time you're guessing positive, 50% of the time you're guessing negative. Okay, that means that this is a classifier, and the classifier true positive rate and false positive rate will be 1/2 each. Okay, because it's just doing random guessing. So TPR and false positive rates are going to be 1/2. Okay. And if there's some other ratio, instead of 50% guess, you're with 30% randomness, you're just saying it's positive. With 70% randomness, you're saying negative. Then it's going to be a slightly different number. It's going to be, for example, 0.3 and 0.3. Okay. And if you're guessing with 90% probability something is positive and 10% probability if something is negative, then it's going to be 0.9, 0.9. Okay. So it's just irrespective of with what bias you're guessing. Okay, you're still guessing. You're not looking at the input. You're just saying, hey, with some probability it's positive, with some other probability it's negative. Then you will only your performance in terms of true positive rate and false positive rate will typically lie on this. Okay, on the horizontal red line. Sorry, on the diagonal red line. Okay, so you can also see two additional arrows. Okay, we just explained this. You also look at two additional arrows, better and worse, and that makes sense because if you it's like if you have a point here, if you have a classifier performance here, let's say this classifier C, which has something like 88% false positive rate and some 20% true positive rate, then you can just take the classifier and then wrap a function around it, which is just the classifier is inside. You have a wrapper function around it and just flip whatever the classifier is predicting to be the opposite of what it's predicting. Okay, so if it's predicting positive, just say negative, and if it's predicting negative, it's just a positive, then you will be somewhere over there. Okay, so which is, I guess, the opposite location here, and that will be a strictly better classifier in terms of confusion matrix. Remember, the intuition for confusion matrix is that you need to have more numbers on diagonal and less numbers on the off diagonals as much as possible. Okay, so by just flipping the sign of the classifier or the guess of the prediction of the classifier, you can get into this region. So this region is of interest to us. Okay. So what happens if classes are imbalanced? We're going to talk about it in a couple of slides, and we'll talk about we'll talk about getting away from the diagonal, as in like this we established as a random guessing classifier of some random bias. So there are other classifiers, C versus A, which one is better, and so on. We're gonna talk about next. Okay. Yeah. So as I just mentioned, points above are better than the random classifier, and points below are worse than the random classifier, and that's why we said we can flip the sign. This I guess we just discussed. Okay. So the question that we want to ask next is the classifier truly significant, or is it just or is it performing better than random guess by chance? Okay. So of course, you can imagine that a classifier in this region, if it's closer to this line here, closer to this red line, maybe that estimated performance is actually not good. Those because we have limited validation data over which we can say how good the performance is. So maybe that's actually overlapping with the performance of the random guessing classifier, right? So you want to be as away from it as possible. That's what I want to say here. Okay, so let's take a break for 7 minutes, and then we'll talk about how to build this something called an ROC curve. So we have not really, an ROC by the name itself is because of historical reasons. So far, we have established a region over which we'll draw a curve, and that curve will capture many different hypotheses. Okay, so let's take a break till 4:36. Okay, so let's resume. So this part of the lecture, at least the next couple of slides, should be easy or difficult depending on if you did the ROC logic in your assignment 3. While you're doing it, at least you understood what is going on. So all of you have plotted ROC curves in assignment 3, right? It was a part of, it was a part of the last question. So let's talk about how to draw this ROC curve. So what we have done so far is saying, hey, accuracy is one number, may not capture everything about the classifier. Let's look at 4 numbers, which is a confusion matrix, with intuition that, hey, the off-diagonal numbers, which correspond to false positives and false negatives, they should be like as less as possible, and hopefully more numbers on the true positives and true negatives. Okay, so that's what we wanted. We have these 4 numbers, and then we started talking about another derived measure called the true positive rate and false positive rate. Okay, so these are just again functions of those 4 numbers. So actually 2 columns. So true positive rate is just true positive divided by true positive plus false negative, and the second one is false positive divided by false positive plus true negative. It's just some sort of ratios for the 2 columns, and you'll see that in fact gives us better intuition, but also has a limitation because we're only focusing on ratios of 2 columns. But we'll get to that point later. So we computed these ratios, true positive rate and false positive rate, and then we started thinking about, hey, if a classifier has true positive rate and false positive rate being 0, 0, what does it mean? If it's 0, 1, what does it mean? If it's 1, 1, what does it mean? Okay. In fact, and so that's how we kind of established this region, that a classifier which has a true positive rate of 1 and false positive rate of 0 is ideally the best one, because it's able to say everything that is correct, and everything that is not correct, or false, or the second class. Okay, so we want to be as close to the top left point there, and we established that this diagonal line here, this corresponds to a random guessing classifier, and it's not just one classifier. So a random guessing classifier with 10% random guess, or 30% random guess, or 50% random guess, so they all lie here. So there are many classifiers. Okay, so each point corresponds to a different classifier, because each classifier will have its own true positive rate and false positive rate, right? So that's what we established. We established the region, and now we're talking about drawing something called a curve. Now you can say, hey, if it's a curve, there's going to be many points on the curve, by definition, and so there should be many classifiers, and so we'll disambiguate that in a second. And so that's what we're going to do now. Okay, so we established a region. Now we want to draw curves, and those curves correspond to actually collections of classifiers. Okay, and we'll see that in a second, and I'll give you some intuition of which classifier is a better classifier. Okay, so all this effort is to just say that based on accuracy, if you want to just say one classifier is better than the other, that is inadequate. And so we're going to still answer the same question, which classifier is better than the other, but using now these ROC curves. Okay, you can use all these metrics. So not just these ROC curves. You can look at accuracy, you can look at confusion matrix, you can look at true positive rates, false positive rates, as well as the ROC curve, which is for a collection of classifiers to kind of get a better sense of where your classifier stands. Okay, so let's actually get to yeah, so we'll kind of, so these two questions at the bottom left that you see, what if classes are imbalanced? We already said getting away from the diagonal, we prefer getting away from the diagonal and towards the top left. But what if classes are imbalanced? We'll address that when we look at some, this construction itself. Okay, and you'll see that when we are constructing the ROC curve, the class imbalance doesn't matter. Okay? So we'll get there when we look at it. So it's basically it's invariant to class imbalance. Okay? So okay, so let me yeah. So how to draw an ROC curve for, as I said, a single classifier just corresponds to 1 point on this in this 0, 1, 0, 1 region. Okay. So for discrete classifiers, as in like something like decision tree, as in something where the parameters are not slightly changed. Like I think of a logistic regression classifier, you can slightly change the numbers theta1, theta2, theta naught. You get a another logistic regression classifier. But for decision trees, you cannot just it's not easy to change the parameters easily. I mean, of course, you have the trees, and so you can of course change the leaves or whatever sub branches of the tree and so on. But basically, for each discrete classifier yields one confusion matrix for hypothesis. So you have a hypothesis, you'll have one confusion matrix that leads to one true positive rate, false positive rate, and 1 point on the ROC region. Okay. Whereas there's all these other types of models, which are models which produce continuous numbers, okay, which produce continuous scores of probabilities. Logistic regression model is one of them, right? So there, each label is predicted by thresholding the output values, and we did that thresholding. I think one of the example cases we did the thresholding with 0.5. So the actual binary label itself is produced by doing the thresholding. So there's an extra step involved beyond just predicting the probability of a class. Okay, and so this threshold is what gives you different confusion matrices. So different thresholds lead to different confusion matrices, and different confusion matrices means different true positive, false positive rates, and that means different points in the ROC curve. So for the same hypothesis, same theta naught, theta 1, theta 2, for example, for different thresholds, you can actually get a full curve. So because you're essentially creating multiple classifiers from the same original underlying parameter set. Okay, so you can choose thresholds depending on whatever the output is. Like if logistic regression, binary logistic regression, you remember the outputs are going to be between 0 to 1, the probability of a true class given the feature. Then your threshold can be between 0 to 1. But if the model itself is outputting, let's say if it's just linear regression for classification, which you did in assignment 2, then the linear regression model can produce any number between -infinity and infinity, which means that you can put a threshold anywhere. So that's what's written here. Okay. So let's actually we'll see one way to construct this ROC curve, and that's just for kind of not it's just an exercise. It's not super important that to know this detail, but let's see how it's done. It's a nice trick. Okay, so we'll see how to get this curve. Okay, so to get this curve, instead of getting the theta naught, theta 1, theta 2, and then just saying, hey, let me now pick a threshold between -infinity and infinity with too many choices, but let's say we discretize it, and then evaluating for everything a confusion matrix and a true positive rate and the false positive rate, and then getting the point. Here, instead of looking at here, we'll just look at the instead of thresholds in the model, we'll just look at models predictions. Okay, so models output, which is generally scores or probabilities directly. Okay, we haven't thresholded yet, so we haven't converted into binary situation yet. We're just looking at probabilities or scores. Okay, so on the left hand side, you can see the scores. Okay, so let's say this is a logistic regression classifier, so it's producing scores between 0 to 1. So we haven't yet thresholded it. Remember, if you threshold it, then you'll get the positive and negative class, right? So let's say we further do another thing, which is sort these examples. Okay, so let's say this is the validation data, and we are sorting these examples based on the scores. Okay, the highest scores is the first one, and the lowest score is the 20th one. Okay, so let's say there are only 20 examples in this validation data. Okay, so based on this, we can incrementally construct this ROC curve, so which looks like this. Okay, we'll get to this curve in a second, but we'll do it one step at a time. If you look at the number, if you count the number of positives and negatives, okay, so this column here, so this column here is the example number. The second column is the true label for this true label for this example. So true label is positive for the first example, where my score happened to be 0.9. Second example, also positive example where my score happened to be 0.8. But there are some positive examples where my score is quite low, but it's supposed to be positive. So you can imagine this one is gonna probably not, it's not a good prediction here, right? So anyway, so this is a true label. And so if you count the number of pluses and the number of minuses, it just happens in this illustrative data. It's 10 each. Okay, so 10 positives and 10 negatives, just for illustration's sake. So how do we construct the RSI curve? So we're gonna start by looking row by row from the first example onwards. This sorted list or sorted tuples here. So so we just dropped the 11th, 12th, 11th, 20th just for sake of keeping the slide clean. They are still there. We just add 2 more columns. Okay, so we have this 20 row table of these true labels and my scores, and then we add 2 extra columns, which is true positive rate and false positive rate. Okay, and we're gonna incrementally compute these. And once we compute, so why are we attaching a true positive rate and false positive rate at the level of an example? Okay, that seems to be like a non-intuitive thing, and that's because what we'll do is think of meaningful thresholds. Okay, behind, so in this slide and next slide, what we're trying to do is really the actual thresholds which influence my RSI curve drawing are going to be pretty much tied to the way these examples are shown here. Okay, so and let me clarify that here. So we start with so the idea is you start from the top and you kind of pause at that observation or that row right before where you're making a change. Okay, so right before you're making a change, so you're flipping from positive to negative, so you stop at row number 2. Now imagine if my threshold happened to be 0.8. Okay, so now we're going to say, hey, row number 2 has like some score 0.8. Let me say, what if my threshold was 0.8 and above to be positive and everything below to be negative? Let's say that's my threshold. These are the meaningful thresholds I was talking about. If that is the case, then if this is my threshold, then I can see that 2 out of my 10 examples, I'm saying it's positive. Okay, right? So my true positive number in that confusion matrix is 2. Okay, out of the 10 that I have, and my false positive rate is 0. Okay, so in the sense that everything else is negative, so of course negative ones are also negative. So my false positive is 0 because I didn't say something which was negative to be positive. Right? So far, if my threshold is 0.8, that you can imagine, right? Any confusion here? Okay, so given that true positive is 2, false positive is 0, and I already told you the number of positives is 10 and the number of negatives is 10, you can easily compute the true positive rate and false positive rate. Okay, so this, because the total number of positives is 10, if true positive is 2, then the false negative is supposed to be 8. Similarly, if total negative is 10, then true negative has to be 10. Okay? So given this, you can easily compute the true positive rate and false positive rate. In fact, that's 2 divided by 10 and 0 divided by 10. Okay, so that means for this threshold 0.8 and above, given this data, which is my validation data, if I choose that threshold, my this particular classifier with the threshold, it kind of completely defines the classifier. It is at this is represented in the ROC curve, ROC region here. Okay, so which is 0 false positive rate and 0.2 as the true positive rate. Okay, any confusion here? Chat folks have any confusion? Okay, so now let's proceed forward. So next we see next we stop again at a location which is row 3, only because there's one more sign change happening in the next row. So we just stop right before the next sign change. So at row 3, let's say we put a threshold at row 3 of 0.7 and say, hey, all my examples with score 0.7 and above, I'm going to say positive, and 0.7 and strictly less than 0.7, let's say I say negative. Okay, so that means clearly I'm making a mistake, right? So at row 3, there is a ground truth which is negative, but if I say threshold 0.7 and above is positive, then I'm making a mistake. Okay, so here I'm saying something positive, which is false. Okay, so the false positive has increased to 1. Okay, so and so at this level, the numbers are going to be 0.2 here and then 0.1 here. So I just move to the left. Okay, so sorry, move to the right. moving to the right is bad, moving north is good, moving to the top is good, right? So you want to ideally reach this point, but every time you're penalized if you miss, do something bad, and so you're kind of drifting away from the point that you want to be, okay, which is at the top 0,1 point. So and then you can see the next iteration, they're all positives in sequence. So till right before we hit the next negative, I'll stop here, and then I'll count how many are the true positives and false positives, basically these rates. Again, I get a number here, and so on. So now you can imagine how to construct this. It's basically a linear scan going on, so it's hopefully not too expensive, and the number of times you may have to check or compute these is basically upper bounded by the number of observations you have in your validation data. Okay? So it's not limited by the original theta naught, theta 2, theta 1, theta 2 stuff, and the number of thresholds you choose is just based on how many observations you have in your training, in your validation data. Or you can also construct the same thing for training as well, but let's focus on validation here. Any questions? Okay, so I think let me in the next slide just repeat what I just showed you in illustration as a procedure. But once we construct this, I want to also we want to talk about, hey, how do we got this RSE curve? This curve, each point on the curve corresponds to a different final classifier setting. Which curve should we pick, right? So there will be some point here which will correspond to highest accuracy. Okay, accuracy is not shown here, but what I'm saying is, if you think of different thresholds, maybe there's some threshold where which you get the highest accuracy metric. Remember, accuracy is the diagonals divided by the off diagonals. Okay. So should we pick that one, or should we rely on the curve to pick some other classifier? Okay, so that's the question here. Okay, and I think we already discussed that classifiers to the bottom left are the ones which are like a little bit conservative in saying something is positive or not. Okay, whereas the ones which are like in the top region basically are more, I guess, we'll say more things as positive. Okay. So the genetic algorithm is as follows: start the predictions, and then iterate through the scores from high to low. Find the next lowest score below which prediction class changes. That is like the right before the change. You look at that row. Set the threshold to be the score value, okay, or the score value is the set of the threshold, and then compute the rates, and then put that point on your 2D region. Okay, so now let's think about the questions that were shown in red a couple of slides ago, which is what classifier, right? So the question is, okay, before going there, question is, does RSE curve always produce a step type of function, right? Of course, the way we constructed it, given the training data and the way we did it, it is going to have stepwise curve, but that's not always the case. There are some corner cases for which you can get, of course, you can get a non-step type of a curve. And I guess the second question is, does RSE curve always reach 1, 1? This question is a little bit easier to answer. So RSE curve will always reach 1, 1, because if you go back to the table here, right? To go back to the table here, if you think of the last entry, like the 20th example, if your threshold is the lowest, if your threshold is this number here, okay, let's say it's 0.1 and above is positive and everything else is negative. With this data set, you can imagine that if everything is, so you're never going to classify anything as negative. Okay, so so your false positive rate yeah, so your true negative rate is going to be 0. So you're never going to classify anything as 0. Sorry, anything as negative. So your true negative rate is going to be 0, or true negatives are going to be 0, which means that false positive rate is going to be 1. Okay, so you will reach. So if your threshold is all the way at the bottom, you are basically already for this point already here, and you will of course also be there. Okay, so you will reach 1, 1. And so this is the question that I think I've been installing for a few slides. So what happens if the class labels are skewed? Okay, so what if there are only 20% positive examples and remaining 80% are negative. So in the previous illustration, we saw 10 positives and 10 negatives in the table that we saw illustration. But what if the labels are skewed? Right? In my whole data set is just skewed, like 97% negative and 3% positive. Right? So what happens? Like, what is the impact of that data characteristic on my ROC curve? Okay. The short answer is there is no impact. Okay. So the ROC curve is, because the curve is actually for every threshold is basically putting a point. Okay. So it is not impacted by the class imbalance. So what are some benefits that ROC curves can provide? So skew distribution, we just said that it doesn't influence the curve itself. Okay. And then what about cost sensitive learning? Okay, so what is cost sensitive learning? As I said, if you make a mistake in terms of false positive or false negative, then there could be an asymmetric cost associated with them, right? If a patient has cancer but you said no cancer, then it's a bad situation. But if a patient does not have cancer and if you said they may have cancer a few times, that's not bad, because they may have, you get extra testing and maybe you don't, you can deal it that way. So ROC curves can take cost information into account, but then they're not original ROC curves that we modified. Okay, but you can potentially take cost information into account. Okay, for making the off diagonal errors. Okay, in the confusion matrix. So yeah, so let's talk about another issue, which is what if we have multiple contradicting examples? Okay, what do we mean by that? This is something that we might have briefly discussed when we talked about KNN, which is that if you have a feature vector, okay, let's say there's in a data set, training data set, you have a feature vector, and let's say the label says positive, and actually here is slightly different example. So you can have another feature vector which can have a label which says negative. For this, sorry, you have feature vector for which there's a label which is positive. You can have the same feature vector and you can have a label which is negative. Why is that the case? Because for the same feature, sometimes the output can be positive, sometimes output can be negative. That's exactly, in fact, what's happening with the logistic regression model. That for the same feature, there's a probability with which it's a positive class. So if you sample from there, sometimes whatever is the probability bias, with some probability you'll get positive, some probability you'll get negative. So that's one angle. But here, what I'm trying to say is that there are 10 examples in the test set, or whatever the validation set that we use, which have the same scores. Okay, so same scores, and it just happens that for 10 examples, 6 of them the ground truth is positive, and for 4 of them the ground truth is negative. Okay. So this is a these are not contradicting examples, in the sense that we are producing the same score for positive ground truth as well as negative ground truth. Okay, slightly different issue. Then the problem is sorting doesn't help, right? If you sort by scores, all these have the same scores, right? And so it's unclear how to sort between these 10. Of course, outside of you will sort according to scores, but for between these 10, they all have the same scores. It's unclear how to order them. Let's say you put all 6 positive examples at the top, and then 4 positive examples at the bottom. Then there will be some then there'll be some some way. Remember, the way we're constructing it is to go up to the example right before the sign change. If all 6 positives are at the top, and then the next 4 are at the bottom, then you'll go up to the 6th example, and then you'll stop there and compute the true positive and true positive rate and false positive rate. Okay. Whereas if the 4 negatives are at the top and then the 6 positives, then there will be a slightly different computation of true positive and false positive rates. If they're alternating, for example, there will be slightly different computations of. In fact, there will be multiple computations of true positive rate and false positive rate. So what I'm trying to say is that the order is affecting, or at least the way we are doing this incremental computation of the ROC curve. Okay. So by which I mean, so think of these dotted lines are the ones which is the problem that we saw in the previous slide. Okay. So if you sort the positives at the top before the negatives, okay, then you will have a curve which is like this. Okay, it will kind of have higher true positive rate first, and then kind of become worse. If you put the negatives before the positives for the same score, then first it will become worse, which is false positive rate is gonna increase, and then it'll become better. And the question is like, what should be the order, right? So on average, the idea here is that you may want to just approximate it like this instead of a step. Okay? Because ordering influences. So one ordering influences like something like this. The other ordering gives a stepwise curve like this. So in expectation, maybe it's the directly joining the points may make sense. Okay. So this, at least this way, it no longer depends on exactly the ordering of this contradicting examples. Okay. Yeah. Okay. So few more points about this ROC curve. So we just agreed that like for each model, we have multiple hypotheses, because once you define the threshold, you actually get the final classifier, and so you have various points, multiple points, right? Multiple points in the ROC curve, and different models can yield different sets of these points. Okay? So different models can lead to different sets of these points or curves, and the question is like, what does a line between 2 points mean in general? Okay, so we're gonna spend the next 5 minutes or so trying to understand. We have a curve, and maybe for another model we have another curve. Okay, because different thresholds for each of these models. We want to understand, like, remember our overall goal is to understand, pick the best model, not just based on accuracy, but hopefully based on these metrics. But before that, we want to understand, hey, what does this what does like a line between two models mean? Sorry, 2 points mean. Okay. So so we saw this idea of a line in the previous slide, right? So when we have contradicting examples at the same score level, but that's not what I mean. What we want to talk about here, we want to figure out like, hey, what let's talk about all classifiers, final classifiers, which corresponds to points on these on a line that has the same slope. So basically, all these classifiers on these ROC curves which have the same slope. Okay. So we want to kind of focus on the slope. Okay, and slope can give us some information about what like what's the trade-off we are doing at that point. So let's look at that through an example. In fact, let's talk about what is the slope, right? So let's say the slope is, let's say we represent it using a Greek letter gamma, so just some number. So so the slope on the ROC curve, remember, y-axis is true positive rate, and the x-axis is false positive rate. Okay. What we're going to do is, let's first subtract the numerators, which is the numerators of true positive rate or true positives themselves. So subtract the true positives. True positive rate, true positive at the second point minus true positive at the first point is going to be equal to false negative at first point minus false negative at the second point. This is just by looking at the confusion matrices. Okay, so because the total number of examples in both confusion matrices is the same, so you can, number of positives kind of drop. Okay, and so this gamma, which is a slope in this ROC curve for any ROC curve at any given point, is true positive rate at the second point minus true positive rate at the first point, divided by false positive rate at the second point minus false positive rate at the first point. This is just the definition of slope, right? So if you have 2 points, subtract the x values, subtract the y values, subtract the x values, you'll get the slope, right? So okay, we write that this way, and so we expand what is true positive rate is just we just so this divided by the total number of positives, and this divided by total number of positives, right? And so we can drop the total number of positives, and so we can write true positive rate minus true positive rate is just true positives minus true positives. Similarly, false positive rates is just false positives minus false positives divided by number of negatives. Sorry, I didn't drop it. This divided by false number of positives is the numerator here, and this divided by number of negatives is the denominator here. Okay. And so why did we do this is because we just in the previous line we said true positive difference is just false negatives difference. Okay. What we're trying to do here through this little bit of arithmetic is to just get gamma in terms of the off diagonal differences. Okay, the off diagonal differences are false negatives and false positives. Okay, and so you can see that gamma is some ratio of off diagonal differences times the number of positives divided by number of negatives. Sorry, number of negatives divided by number of positives. Let's actually drop this, somehow. So let's say number of negatives is the same as number of positives. Let's say we are in the very balanced classification setting. There's no imbalance. Okay, so now let's interpret what's going on. So what does the slope of that rock curve mean, right? So if the slope, let's say gamma is 10, okay, what does it mean? It just means that like false negative, the difference in false negatives is about like minus 10 times the difference in false positives. Okay, so what does it mean? It means that getting one more false positive, so one extra false positive here, is equivalent to losing 10 more false negatives. Okay, because the relationship between the difference in false negatives is minus 10 times the the difference between false positives. Okay, so if you get one extra unit here, then that leads to like minus 10 extra gap between the false negatives. Okay, so one minus 10 extra or losing 10 more false negatives. Okay, and if gamma is 0.1, then it just means that getting 10 extra false positives is equal to losing one more false negative. So we are talking about numbers which are off diagonal numbers. We are really talking about how do these two trade off. Okay, so as you're on the rock curve, if you have the slope which kind of varies, if you remember, it varies. For example, slope is high when you're in the bottom left, and slope is low when you're at the top right. Okay, so you are actually trading off between false negatives and false positives. Okay, more false negatives, less false positives, and less and vice versa. Okay, so that's what you're trading off between the off diagonal terms in this setting where you have balanced labels. So in some sense, you can think of this gamma as a mediator between the cost of false positives, and the cost of false negatives. Okay, so you say something is positive when it's not the case. There's some cost, and there's some cost for you say it's negative when it's actually the truth. Okay, when it's actually let's say cancer or spam. There's a cost, and those two costs you can relate by saying, hey, there's this gamma factor, okay, which is the slope on the ROC curve. So depending on which part of the region you want to pick classifiers, there's a gamma that you're basically picking, and that gamma influences how you're trading off between false positives and false negatives. Okay, so let's look at. We'll come back to this cost difference in fact right here, but let me talk about. I've been talking about multiple ROC curves, so let me draw four different models here. Four different models. Okay, A, B, C, and D. Four sets of classifiers. Okay, sets because each classifier, depending on the threshold, itself is giving a different final classifier. Okay, so each curve. So A curve is like this. Okay, it's like the parameters without the threshold choice, but every time you choose a threshold, it's one of these points here. Okay, and so A curve is like this, B curve like this, C and D. Okay, what you can do with this diagram is you can draw a convex hull. Okay, so a convex hull, it's called ROC convex hull. CH just means convex hull. What is a convex hull? Just think of like putting a like a cloth on top of these curves. Okay, where the cloth cannot like become wiggly. Okay, so it can be only in the shape of a convex object like a ball. Okay? So you can see that this gray area, so the region you want to focus on is here. So you are kind of matching A curve, and then you're becoming flat. You're not going down, but you're becoming flat, and then you are hitting the C curve and then going till there. Okay, so what is convex here? So this region here, this shaded region, is called a convex region. It just means that if you take any 2 points in that region, any 2 points in this region, draw a line through them. Okay, that line will never be outside the region. So and you can imagine, like, you can look at this, right? So if we take a point here and here, if you draw a line, it's still in the region. If you draw any line, in fact, any 2 points there and draw a line, you kind of hard to figure out. In fact, it's not possible to find a line which is with 2 points inside the convex region and a part of the line outside the convex region. Okay, that's what a convex region means. Okay, so why are we looking at that? The idea is that this, if you look at the convex hull, the curve B and D are not contributing ever to this convex hull. Okay, you can see this boundary of the convex hull, because the other boundaries are not relevant, not interesting, because this boundary is where all the curves are. So B and D are not touching the curve. Okay, so what does it intuitively mean? I mean, intuitively for this slide, but you can actually kind of formally do that later. Is that means that B and D are always going to be suboptimal choices. So whatever choice configuration that you pick for B or D set of classifiers, you can actually do better by picking A or C or a convex combination of A and C. Okay, so convex combination of A and C just means, for example, if you want to pick, here's B is performing really well here compared to everybody else, right? This black curve here. So what you can say, hey, B is performing well, do A and C match it? Okay, and the answer is yes. You can match A and C to this, to do better than this, better than B here, like a point here, by just taking a convex combination of those two classifiers. Okay, so just a convex combination just means a weighted average. Okay, so 0.6 times A plus 0.4 times B. Okay, some weighted average. Okay, so that's a convex hull. Yeah, so let's come back to this notion of this slope again. Okay, so convex hull was one aspect where you can compare multiple sets of classifiers, but I want to come back to this notion of this gamma slope that we have. Okay, so because that's going to help us pick one of these classifiers. Okay, so what specific classifier should you choose from, let's say, A or C or both? Okay, so the choice is really dependent on the application. And so two canonical applications that we have briefly mentioned in this lecture is SVM classification and cancer classification, cancer detection. So for SVM classification, classifying spams as regular mails is okay. It's annoying a little bit, but it's okay. So although the ground truth is spam, ground truth is positive. Ground truth is positive, but you are classifying them as regular mail, which is negative, right? So these are false negatives. Okay? So false negatives are okay, but classifying regular emails as spams is very bad, right? If you get a job offer email and then that's posted as spam, it's pretty bad, right? So false positive is critical. Like, you don't want to have too many false positives. You want to have, you're okay with many false negatives. Okay, so cost of false positive is much greater than cost of false negatives. Okay? So this is a preference that you can impose on in this application. So because you have this preference, you may choose on that curve being somewhere, okay, being on the bottom left or the top right on that curve. And we'll see in a second where it will be. Similarly, the opposite case is cancer diagnosis, where if you have a healthy patient and you diagnose them as cancer, okay, so that's a false positive. That's okay. I mean, in a sense that it's not okay, the person has to go through tests, but at least it's better than if they have cancer and you say they don't have cancer. Okay, maybe then there will be a problem, right? So here the cost of false positive is much lesser than cost of false negative. So cost considerations are an external metadata that using which we're going to decide which point on the ROC curve or what the right threshold, for example, to pick. So if you look at, so just continuing from the previous slide, if you look at A and C, for example, there are two models. And if you have a spam-like problem where cost of false positive is much bigger than cost of false negative, okay, then you want to be close to like bottom left. Okay, so you want to be close to bottom left, okay, because you don't want to incur false positives at all. I mean, you can imagine, right? So x-axis is false positive rate. So the more further out I am on the x-axis, I'm doing pretty badly. Okay, so you want to be as close to 0 on the x-axis, okay, and you can see that probably thresholds or whatever, some configurations here are better, okay, so with high slope. Okay. Similarly, the cancer-like problem where the opposite cost of opposite metadata, opposite information, where cost of false positive is actually not much, okay, not as much as false negative. Okay. In that case, you are fine at, hey, x-axis is false positive, I don't care too much about false positive, let me go all the way to the right here, and so you can pick something which has a decent amount of false positive rates, but has high true positive rate, because if you have high true positive rate, then you'll have low false negative rate. Okay, so so those are choices you can make. And let's talk about label imbalance, right? So let's say the number of negatives is like huge, much higher than the number of positives. Okay, so where does that fall in? So you have a huge number of negatives and very less number of positives. Then, but you still want to detect. So think of, in this situation, let's say my very dumb classifier just keeps saying, hey, everything is negative. Okay, says everything is negative. That means my true positive rate can be 0, right? My true positive rate can be 0, right? So I'm going to do pretty badly if I have a dumb classifier which always says everything is negative. So what I want to do is trade off between negative and positive. So what I can do is pick a point which is actually over here, okay, which have very low false positive rate but high true positive rate. So something like here would help, which is not the same as a high accuracy classifier. Okay. High accuracy classifier will be one which will say everything is negative. So you will not have true positives. True positives is 0. So which means like you will pick. So high accuracy classifier will be something like very close to the bottom somewhere here. Okay. Basically the where my cursor is, but you want to kind of increase that true positive rate. Yeah, you need to increase that, because otherwise you are saying everything is negative, which is not a useful classifier. And so you can use this type of intuition to pick the right threshold. Okay, so accuracy is not the right number to report, especially not the only number to report. Maybe it's useful, but it's not fully useful. So you want to kind of use a ROC curve to decide what's the right threshold and therefore the right classifier. Okay, and so you have to trade off the off diagonals. Okay, so there's a related idea related to ROC curves, which is called area under curve, which gives you a sense of the average performance of this set of classifiers. Okay, so if you remember, there's a bunch of thresholds which lead to one curve, but if you want to, on average, figure out the performance of the model or the collection of classifiers, then there's a summarizing number. Okay? So it's not, so it's, again, this is now getting desensitized to the class imbalance aspect. Okay, if you have a specific problem, there's a specific class imbalance. AUC is again not a good measure to talk about for that. Okay, but it's an average performance of your classifier. So it's basically a number that summarizing number is just a number between 0 to 1. Okay, it's basically the number should be ideally greater than 0.5, and the highest number will be 1. Okay, it's just the area under it's area under the ROC curve. Okay, so if you remember, the perfect classifier is something which is on the top left, which has a false positive rate of 0 and true positive rate of 1. Okay, what would the area of that curve? It will be 1. It will be 1 unit, right? So it's just a whole full square. So 1 times 1 is 1 area. Right? So under random classifier, if you remember, it was on diagonal. So that area is the lower triangle, 1/2. Okay? So AUC 1/2 or below is terrible, and AUC 1 is the best you can achieve. So in between that, it gives you a sense of an average performance of the classifier, very similar to the accuracy number. Okay, so they are kind of comparable. So you might have seen people report accuracies and AUCs. It's just average performance. Okay, but technically, it has an interpretation which is the probability of you. So if you remember validation data, you have a bunch of positives and a bunch of negatives. It's just saying, hey, if you pick a random example which is positive and random example which is negative, and then if you look at the scores, what's the probability that the score of the positive guy is better than the score of the negative guy? Okay? So that is exactly what AUC is. But if you just but it's basically, if you just mechanically want to think about it, it's just the area under the curve. Okay, so here's a simple diagram. So B and A. So here, which classifier performs better than average? The answer is, I guess, B, because B has more area under the curve, so it has a higher AUC value. But yeah, so if you have let's say B is this yeah, so if you say B is this specific set of classifiers, let's say they're discrete classifiers, so actually taking specific values here. Sorry, not discrete classifiers, but scoring classifier. So remember, scores were produced and then you pick the threshold to construct this. And then A is one of these thresholds. Okay, so if you take up one of these thresholds, then you can report AUC for you can report AUC like this. So one of these classifiers will have slightly smaller AUC than this collection of classifiers. Okay, so implications of ROC beyond accuracy is exactly the following, right? So deal with basically being able to balance false positives and false negatives, and it's insensitive to the changes in insensitive to class imbalance, whereas accuracy is sensitive to class imbalance. So you can find a good model using this ROC convex hull idea, where you can deal with and where you can deal with a convex combination of existing classifiers, as well as deal with the imbalance ratio, where you prefer things to be on the for example, there are very few positives, then you prefer classifiers which are on the which are on the left and bottom of the curve. Okay. Yeah. So an AUC summarizes average performance, very similar to accuracy, and so using AUC is not a good substitute for ROC. So it's not like we went through all of ROC stuff and just kind of start reporting AUCs, because AUC has similar issues to accuracies. Okay, so for example, high AUC classifiers can perform worse in some regions. Okay, and those regions maybe are important for your actual data set. So in your actual data set, if the number of positives is like 3% of the full data set, then looking at AUC number is misleading. It's very similar to looking at overall accuracy number. Okay. So any questions about this slide? So we did ROCs in your assignment 3, but hopefully this discussion so far has clarified a few things about the choice of the model that you can do. How to think about the choosing of a model depending on application, basically. Okay, so I guess here we're just asking some questions like low false positive rate imply that most positive predictions are indeed correct. That's not true. We know that false positive rate being small doesn't say anything about the y-axis, right? So, and that kind of says something about a next set of measures we'll look at next class, which is precision recall and precision recall curves. Okay, which is that ROC curves, ROC curves are actually looking at two columns of the confusion matrix. Okay, if you look at the true positive rate and false positive rate, they are two they can be computed using the collection of numbers of the first column and the second column. Okay, but what it misses is the following, which is the fraction of which is the which is a measure which I think we'll define next class, which is called precision. Okay? So precision is a number which is true positives divided by how many did you say are positive out of all the things that you said were positive. Okay, so let's say you are the classifier. So let's say a classifier produces 50 predictions, out of which 20 it says is positive. Okay, so out of the 20 things it said positive, how many of them were actually positive? is the ratio here. Okay, the fraction of positives. Okay, how many were actually positive out of all the things that you said are positive is the fraction of positives, and there is a problem with that number. Okay, so this number is actually linking those two columns. Okay, so true positive is, remember, is the number on the top left of your confusion matrix, whereas false positive is the number on the top right of the confusion matrix. Okay, it's linking rows. Okay, and that view was missing from the ROC discussion. Let's say the true positive rate is fixed 0.9, and let's say the false positive rate is also fixed at 0.01, which means that the classifier is exactly like really low false positive rate and really high true positive rate. It's really at the top. Okay, very close to that curve. The question is it a good classifier or a bad classifier? And that really depends on fraction of positives. Okay, so which means that the class ratio, how many positives are there in my data. Okay, so if my data is fully balanced, then if you actually look at a slightly different ratio, which is this precision ratio, then the precision is actually 0.989. Okay, so how did you get this? True positives is 0.9, 0.9, which is this true positive rate, times how many positive examples are there, which is 0.5 times m. Remember, it's 50% are positive, and that's how I got the denominator as well. So I got a ratio of 0.98 as the fraction of positives, or the precision, when the class is balanced. Okay, when the data is balanced. But when the data now becomes imbalanced, let's say when the number of positives is 0.1, this precision is decreasing. Okay, now the precision is 0.9. Okay, when there are only 10% positives. Similarly, when there are only 1% positives, then the precision is 0.4. And when there are only less than 1% positive, then the precision is like 0.08. So precision is decreasing for, although we are seeing high true positive rate and high false positive rate, and depending on the class composition, we actually have low precision, and precision may be important in some applications. Okay, and that leads us to a discussion about precision, recall, and some other measures. But just think of it this way, right? So in confusion matrix, we have 4 numbers: true positive rate and false positive rate, which we use to define ROC curve, are specific functions, specific 2 functions, summarizing numbers, 2 numbers. Originally, we had 4 numbers. We summarized it 2 numbers. Of course, there's going to be some loss of information. So just based on those 2 numbers, we should not be able to say everything about our classifier because there are originally 4 numbers, right? So basically, we'll create 2 additional numbers, which are precision and recall, to kind of counter this, and then talk about, and so that will give you a much more complete view of the classifier, of any classifier, or classifiers, compared to just a ROC curve. Okay, so with that, let's pause here and pick it back up next time. So next time we'll talk about, so we spent 2 lectures on model selection and assessment, only because there's a lot of thought process. Okay, of course, in terms of practice, it's very easy to do k-fold cross correlation or whole cross correlation, or even plot ROC curves, but there is a lot of choices you're making implicitly, and there could be places where you're going wrong. So next lecture, at the beginning of the lecture, we'll briefly discuss precision and recall curves, and then we'll jump into generative models and unsupervised learning, okay, and nuances there. And we'll not try to, as I said, we'll not try to do breadth. We'll pick up popular models there and really discuss them in detail. Okay. Okay, so let's break. Oh wow. Okay, so there are several questions online. Okay, so let's